Today, we'd like to present very briefly part of the work that we have been doing in the last 3 years. And before doing so, I would like to introduce my team. So we have been in Oxford for the last 3 years, maybe most of the time in lockdown, but we have been very lucky to being able to keep healthy and also to being able to continue doing some work. We're very lucky last week to being able to meet for the first time in many months. And I would like to mention here the people that has been doing the work that I will be presenting today. So Tom Alistair, our PhD student. Tom recently defended his PhD. We have also Hanwen and Tristan. They are PhD students starting also in the group. And we have previously been very lucky to have Joe as a master student. So all of them are the people that are really behind the work that I will be presenting today. So very briefly, for those that don't know us, we are really focused on computational organic chemistry and very much interested in understanding how chemical bonds are formed and broken in different reactions. And we do cover different areas instead of the application, but also the size of the system that we look at and the tools that are used, going from very small molecules in solution to more complex reactions in enzymes. And really, we try to take a similar approach in all cases, trying to understand the smallest possible model, looking at the fundamental chemistry that is taking place there, and then understanding how different effects, for example, solvent, a catalyst, or an enzyme are affecting selectivity and catalysis. And in the last few years, also, we have been quite active in developing different computational tools to facilitate our daily work, but also to facilitate the work of many experimentalists that are very keen to explore a computational chemistry as a tool to be used alongside an experiment. So among them, we have developed computational tools to speed up the design of supramolecular cages, also to study reaction pathways, and more recently, machine learning potential for studying chemical reactions in solution. It will be these last two topics that I will be discussing today. But before, I will just mention a bit of the motivation and where we are in the area of computational organic chemistry. We were just looking before that we think that we have solved how to make a compound that is very important in drugs, but actually how to make bonds, specifically highly selective, remains a challenge. And computational chemistry has contributed hugely during the last 100 years almost in understanding chemistry. So we think of the initial type of models that we have in the 40s and 30s, where we have the starting of physical organic chemistry, where many of the knowledge that we use today come from. So understanding came from these back of envelope models, trying to predict selectivity and in different chemical reactions. We then moved in the 80s and 90s to density functional theory, now widely used, and many of the people using that, such as Ken Howe, really led the move from physics to chemistry, using those tools to explore organic chemistry reaction and really providing a rationale for how reactions are happening in solution. And more recently, we see machine learning being used for retrosynthesis predictions, among many other tools. And we tend to see that as a linear timeline, but actually we feel, and personally, that is our approach, really combine them, because many of the advantages of machine learning are also limited by the lack of understanding. So for example, combining those understanding with the back of envelope models, physical organic chemistry tools, we see that is the best of the different worlds that we can combine. So in the group, we tend to use a combination of them, and we have different expertises alongside, because even though we promise that we can predict and provide understanding, while understanding is very well covered, predictions are very, very challenging. And the reason for that is because many of the simple processes that we see in solution are very challenging. So for example, how we describe properly solvation, entropy, even electronic energy now is becoming much more easy to obtain high quality electronic structure data, but then we lack conformational sampling. So we still have many challenges to face to be able to say that we can certainly make predictions of new chemical reactions and new compounds. So trying to address some of these challenges is that we have been motivated to explore different areas. And today we'll just focus on two main projects. One is related to automation of reaction pathways, really trying to tackle how we can improve in automation, but also how we can make use of the advantages of electronic structural methods and conformational sampling to really obtain high quality reaction pathways. And later we present briefly about machine learning potentials for chemical reaction. I think that in the first presentation, we had a very nice introduction of how machine learning potentials can be used for modeling. And I will be focusing mostly on reactive potentials and small molecules. So let's get started with the first approach that is very much looking at reaction mechanisms. And many of the computational chemists, mostly computational organic chemists, will spend many days trying to optimize transition states and explore a reaction coordinate. But actually, more recently, that has not been maybe needed. We usually have seen that with machine learning, we have the possibility to explore retrosynthesis, forward and retrosynthesis, just using a SMILE representation. So we can identify if a product will be formed or which are the reactants that we need for a given product. And we have different approaches that really allow us to map one-to-one those systems. But still, we see a value in exploring those mechanisms because we don't want to only tell the computer to tell us what to synthesize, but how the reaction is happening, mostly because we can still do design from that understanding. And what we usually want to calculate is an energy profile like this one, where we have a reactant, transition state, and products. And from that, we can obtain the kinetics of the process and the rate of reaction. We can also obtain information about the thermodynamics. And usually the way that people have been doing that for the last 40 years has been mostly divided into three main approaches that we classify. Chemical intuition, and that is really, you have tried so many different transition states that you have in the back of your head, the different values that you expect for. Singlet-ended method, where you provide information of the transition state, of the reactant and product. So only the reactant and then you proceed, or the double-ended when you provide information of the reactant and the product. I will just briefly define these last two. So the single-ended method has been very popular and promising, mostly by people like Zimmerman, and also other contribution from Todd Martinez, for example. So the idea is very interesting. You have a reactant and you tell the computer, please find all the pathways that you can find for this starting material. And this is very, very powerful if you don't have any knowledge of the potential pathways that your reaction can follow. But it also means that you have to explore many different possibilities. Some of them you know in advance that are very unlikely just through chemical knowledge, but you still spend time in exploring all of them. So which means that those approaches are limited to just a few heavy atoms, but still very powerful if you have no knowledge of what is happening. In most cases that we explore or interact with experimental chemists, we know more or less which are the potential pathways. Identifying side products can be giving us some insight also about potential pathways to explore. So we can usually at least guess which are the potential reactant and products, and from that give that information to the computer and explore a full reaction pathway. And that has been done previously by different people with different flavors. The more well-known maybe is the one that is implemented in Schrödinger. But when we were exploring all of them, we found some limitations and really wanted to address those in a very simple way. So we wanted to develop a code that will be possible to use with organic and organometallic reactions. So far, only organic reactions were tested. We wanted to make transition state finding and sampling automated. So in previous approaches, finding was automated, but there was no possibility of sampling, which is very limited if you have a very floppy system. In most cases, that was limited to a single electronic structure package. And in some cases, you had to pay for that, and we couldn't afford paying anything of that type. So we really wanted something free that will be compatible with any electronic structure package that you have. We have covered quite a lot. We still have many to cover, but I hope that with AutoD, we have included many of the functionalities that we hope will be useful for the community. And this is a very short workflow that I will be just describing very briefly in the next few slides. So the first aspect I would like to mention is conformer search, because that has been something that we have been increasingly aware of the importance of sampling the conformational space well. And we know actually that for organic molecules, RDKit work very well. So I was definitely keen in voting for RDKit because it has been so powerful and useful. And actually RDKit is behind AutoDE. So many of the tools that make possible AutoDE to be free, so there are many tools that are free out there, and we can just join efforts and combine them. But actually with metals is very difficult. So we did have to develop a new way to obtain conformers for metals complexes. And that is based in a repulsion bonded term that is a very simple, has no quantitative meaning. Our goal was simply to obtain meaningful geometries at the start. And we're testing our approach with those provided by RDKit and by OpenBabel. So in many cases, what we did was taking the Cooley group but database of metal complexes. We're using a small representation initially and process that through AutoDE, obtaining those conformations. So you see that AutoDE in many cases, in all the cases was positive, but RDKit in some cases give you very flat conformation, and maybe you're familiar with that you process that through RDKit and you just have all the atoms in the same plane. With OpenBabel was a bit more tricky because was not able to recognize the smile string. So Joe, one of the master students, and Tom were really writing a wrapper to work out how to make interpretation of the smiles and really generate the atom, the molecule here atom by atom. So that is what we're doing. What it means is that we are losing some of the stereochemistry that was input initially, and that is something that we are currently aware and trying to fix in this case, because the way that we do is that we add atom by atom and we're losing that information. In general, with organic molecules, RDKit works perfectly, and we have been using that very, very happily in most of the cases. And how do we then identify? So we have the reactants for the reactant, we have the product, we have the lowest energy structure for each of them, and then we want to map the TS. So how we do the mapping? And this is just for a Claisen rearrangement. And what we do is identify the number of bonds that are formed and broken. And to do that, we do draw a graph representation of the reactant, a graph representation of the product, and we count the number of bonds. So then we can identify that the difference between reactant and products is that there is one CC bond that is formed and a CO bond that is broken. CH bonds are not affected. So which means that of the all combination possibles that we have, we don't have to try all the combinations. We have only to try those that are indicating a carbon-carbon bond being formed or a carbon oxygen being broken here. And then when we identify those bonds that are affected, so we have the formation of this one, breakdown of this one, we identify those that are isomorphic to the product. And among them, we identify only one. So the labeling of this graph is very fast. And from that, we can identify the bonds that will be formed and an idea of the reaction that will be taking place. We have a limited number of bonds that can be formed or broken, but so far we have seen that that has been sufficient to cover most of the chemistry. And then we have, once we start the optimization of that transition state, we have an initial guess, and then we provide that initial conformation to the electronic structure package that we're using. We're introducing different ways of optimizers to get a better representation early on in the system, but so far will very much depend on the electronic structure package that we are using. Something that is very important to consider is conformers at the transition state. That is sometimes not very common, or still in organic chemistry not so common yet. And it's very important because you can see here that a reaction that is giving you the most stable product is not necessarily the one that will be connected to the lowest energy pathway. So I think that it's very important to sample both reactant and products, but also the transition state. And we identify, we do the sampling of those in the same way that we were indicating, the same energy form that we are using before with some restraints. And these constants that we're mentioning here are really based on kind of empirical estimates that we have with some reference distance coming from the Cambridge database. And then later we can see this is an example of how the input will look like for an SN2 reaction. So this is our input file. We define early on, and you can generate that in your own computer, which software you're using and so on. But for this particular reaction where we have defined all these configurations, we really have to define the reactants in a SMILE representation and products and indicate if you want to calculate the complex or not. And then the program will give you an output, a PNG file with the figure of your plot and also a log file with energies. So the student that was working on this initially, the master student, was timing himself and checking how long it will take. And the SN2 reaction is not difficult to calculate, but still waiting for that to finish was taking up to 2.5 hours. Just drawing the plot and all these small, tiny, simple things, but they take time. And actually, we can really reduce the time by introducing automation in those cases. So we can really see the value of that when you are considering many different transition states at the same time. We have used that to explore a natural product. So this is a much more complex system, and just providing the SMILE representation at the start and making it do the work, you can identify the lowest energy pathway, which is due to this hydrogen bond interaction. So the program can really identify the lowest energy conformant, but also the correct packaging state of this ring. We have used that for multi-step reactions. The only thing that we have to do here is provide information about these different intermediates. So having chemical knowledge is very important. AutoD will not find new system. May happen that the optimizer just go in the other direction, but in general, it really needs the knowledge of the chemists of what can be possible or not. This is just an example from the Morikuma and Howe group, where they were doing both automation and manual work in this case, and took them a year to complete this work. It's very important that most of the time was spent in actually searching for potential pathways, which is again the chemical knowledge that is still needed, but we're able to do in a very much in a day once you have the possible pathways there. Now we can use that for metal complexes. Still, the stereochemistry is something that we really like to tackle, but so far we can do multi-step reactions with metal complexes as the one shown here. So we are very happy with it. Software so far has allowed us to do work more efficiently, but still there are many limitations that we know, some of them based on graph representations and the condition of isomorphism. So for example, an isomerization is not possible. We still have DFT as the main bottleneck, and solvation has been very difficult to implement. Implementing is relatively easy, but having meaningful results from that implementation of explicit solvation remain really a challenge if there is no proper sampling. And there are some new developments to introduce transition state optimization in a much more simple way, developing new building blocks and wrappers for other packages. But at the end of the day, the bottlenecks come usually from how good the optimizers of the program that you're using is at the end. So that with DFT being the limitation and in many other systems, that leads us to the other project that I wanted to briefly mention in the last few minutes that we have left. And this is related to machine learning potentials. I know we have heard before about the different flavors of them and how they really promise to compensate the challenges that we face with classical molecular mechanics and with normal DFT. So if we see the computational cost here, we see that MM is usually very cheap, force fields are very cheap, but actually the quality of them is very low, especially if we consider for reactions, because they were not developed for that. So what machine learning potentials promise to do is have a very low computational cost, but have the quality that can be even higher than DFT. And that is something that we have been trying to show, and that we saw in the first presentation too, how we can really go close to coupled cluster with machine learning potentials. I will go just briefly on what a machine learning potential is, because that was described much better before. There are different representations. So usually the way that we choose is how do we represent our system. We give this representation to a regression approach that can be either kernel-based or a neural network. And from that, we obtain energies and forces. And if we have energies and forces, we can propagate dynamics. So what we have been doing so far is using a kernel-based method that is the gap approximation potential developed by Gabor Twan at the University of Cambridge. So actually the idea of using those potentials came when I came to Oxford. He gave a presentation here, and we were showing him this system that we wanted to model with solvent and completely. This is a metallocage with palladium +2 and has a ligand inside. So we really wanted to look at the dynamics. We knew that classical potentials were a bit limited, but I wanted to explore that. So he suggested this is the solution. And we really went for that because I have been exploring before QMMM approaches, classical reactive force fields. Most of them seems to be easy to use, but actually each of them has an art in itself. We hope that machine learning potential will be much less than that, but still we're learning on that process. So I was really, really keen to try alternatives to what I knew before. So there were a machine learning potential that we have seen before is the ANI potential developed by Adrian Royberg and colleagues in the US. And we have been using that. It's a great approach. It's very general, but it's limited in the type of atoms that we can use. So if you wanted to retrain the network, that meant computational time that we just didn't have. So we went for the approach that Gabor suggested. A gap approximation potential is not transferable, but actually training is so efficient that we really can target that to the system that we are interested in. So we went for that approach. And so far, there has been ANI, probably the most popular potential, but actually there are other potentials that have been used to study chemical reactions. Some of them has been, most of them, as you see, they are neural networks, but with time you have seen that the number of configuration has been decreasing. So huge number initially has been decreasing so far, but still there are thousands of configurations that you need for a single system. So that was a limitation. We really wanted to have a black box approach that would allow us to say which molecule we want to train and that have a potential in a day. GAP has been used extensively, especially in the UK, for modeling elemental materials and organic molecules, but we didn't have examples of doing that in a reactive fashion. So that is where our contribution came. So we are testing initially, learning from them the standard approach. We have a training, we have a validation test. And this is the error, is not great, can be better, but we were quite happy in many cases saying, okay, we have a low error. But what we saw later is actually that validation that we were doing, splitting training and tests, was not giving us good potentials. The potentials were just exploding very quickly after a few femtoseconds. So we really have to plan better how to identify what a good potential would be. And in general, what is a good machine learning model? It's not just having training and tests, but really having prospective validation as well. So we identify this error metric that allow us to identify how quickly our potential is accumulating error. So it doesn't matter if we once in many femtoseconds, this simulation has a high energy and force, that will be accounted and penalized. So we have this counter of how stable our potential will be. So we use this metric combined with separation of inter and intramolecular terms that was key to make these reactive potentials stable. And we're able to finally, using that approach, model our metallocage that I mentioned before. So far has been gas phase, but we're very happy to have at least that and as a starting point for introducing solvent. And what was very interesting here is that we didn't have to model the whole cage. Using symmetry, we can identify rather than 140 atoms, we have so only 68 atoms to use for training. So that was sufficient to have a stable model where we can identify and look at the flexibility of the system and compare that to classical force field. So we knew that the classical force field was much more floppy than the one that we expected. We have been looking at chemical reactions, and this is the motivation that we have so far, looking at different types of reactions. So the symmetric and asymmetric SN2 is a very simple process, but was just to showcase our methodology that we can use GAP and really reach coupled cluster level. So we can train with PVE, but also improve on that with further training with coupled cluster and have coupled cluster quality at a much lower level. We usually train from the transition state, but that is not needed. We can train from the reactant and start with active learning, exploring different areas of the reaction pathway. And that has been really useful for us moving forward. So this has been our first introduction to including solvent around the system. So this is a water solvation, and we can propagate dynamics from the transition state going to reactant and products, and even see recrossing in some cases. We can train that in a day, and that was very important for us. We wanted something efficient, something that people, organic chemist modeling, hopefully in the near future will be able to use, and having that fully automated. There are many challenges, and we are working on that, and people that want to contribute, we're really much looking forward to doing that. And with that, I would like to thank again my group, Volker and Gabor, that has been introducing me to GAP, Adrian Reuter, that has been super helpful helping us with Annie, and they have been doing great work there as well. Just finally, just mentioning that we have different tools available online. We have been very lucky to be working in an era where we have open science, and that has been hugely important for our work to be known by others. And finally, we have an open position, so anyone that will be interested in discussing, please contact me. And thanks again for the recognition to my group research. Very much appreciated.